So you can learn stuff when you try and figure out how to do things.
How does that waste that time?
Because that's a lot more money.
So obviously, right,
Yeah, but I mean,
there's super smart, like 17-year-olds trying to do nuclear fusion, but they're super smart, like lots of people trying to do nuclear fusion. Because it would be great if we could do it. And I know I'm being redundant. It would be great, right? Higher energy density than nuclear fission, right? Which is super high already. Products that aren't radioactive, right? Helium is very radioactive. So it would be fantastic. But we just still can't do it, like Taylor said, we can't do it getting more energy out of it than we put into it. So this has been researched for over 50 years, right? Probably significantly longer than that. We're not very close to doing it economically. Yes, there is such a thing as cold fusion, which we're further away from being able to do than hot fusion. So what we're closer to being able to do is having really hot deuterium and tritium, having a high density plasma, right? So we're stripping electrons off, we have charged stuff. So we can do that, but we do have to maintain those high temperatures. To keep that a high temperature plasma, we have to confine the plasma, which is tough, because charged things like to do chemistry. So I know we've talked about magnetic fields already, or what we use to contain that charged stuff. So we can do that, we absolutely can, and we do it, but we just can't get the energy out that we put in to set that up. The sun can do it, right? The sun is able to maintain that high enough temperature to keep stuff, and it's big enough that it can use gravity to keep the plasma confined. The sun doesn't have to use magnetic fields. Yes?
What was like, didn't some guy say like he did cold fusion and then they tried again and it didn't work?
I mean, I think people have attempted and done cold fusion, and I don't even quite remember what it entails, but I'm not surprised to hear that it's tough to do and might be hard to replicate. I'm not surprised to hear that. So that's nuclear. So we actually spent kind of a long time on nuclear. We're only going to be spending like less than a class on our other means of producing electricity, but that's fine, right? Because we don't have any others besides maybe hydro that make up a significant chunk of our energy budget. So we probably shouldn't have any that make a significant chunk of our class time either. Right, so we're going to try and get pretty far into solar power today. And there are two extremely distinct types of solar power. There's one that relies on photovoltaic cells, so often that's called solar, like PV for photovoltaic. And then we also can generate energy using solar heating panels. And we can do both of these on like small scales or on large scales. So for photovoltaics, right, probably some of you have small scale photovoltaics in here. Does anybody? Yeah, Miles is reaching for the calculator. Yeah, you gotta give it a graphing, all right? But some of us have solar power calculators, right? So that on a small scale, and that has a battery too. But on small scales, can do photovoltaic. On big scales, right? There's where's the solar farm? There's one.
Tinton Falls.
Oh yeah, I was gonna say Eaton. I think Tinton Falls from like Wyckoff Road. You can see pretty big solar farm. You don't even have to go that far, right? You go. Get confused. Go that way. That way, right?
It's that way.
I think
It's
it's
on the
true.
parking lot.
The parking lots, right? Like on the one side of the ag building, or actually both sides of the ag building.
What do they use that for?
What do they use that for?
Is that for like the ag building, or is that for like charging cars?
No, that's not charging cars. No, that's not charging cars. No, Jake.
Central High School has like a huge amount of them just at their
A lot of
Raritan.
Long Branch, Raritan.
Yeah, so we can, let's talk about this. Does anybody have solar photovoltaic at your house? Going to?
My neighbor does.
Yeah, so like my wife and I met with somebody a few months ago to talk about it. So there was something that was a little, what's the right word? Offensive, I guess is the best word I can come up with. So New Jersey state law does not allow you to put in more solar panels than you ought to be able to use yourself. Right? So like if you have lots of property, you're not allowed to just fill it with solar panels, right? New Jersey state law says you can't. Now, why?
They don't want you to
Even the energy companies.
Because the JC. PNL and the people that have the coal plants and the
Businesses
vision
want to
plants,
have
right? They don't want to lose all that money by people generating their own electricity. So we have a state law that says you can only have small things up. But if you're a government entity, yeah, fine, whatever, you can do what you want. Like they're like exempt from that state law. So yeah, that's why governments can put up way more than we can. Now, I actually asked the guy that we met with about this Tinton Falls one, and he said he didn't know, but that there can be agreements that if you're selling that power to like a business or like one particular end user, then there might be some loopholes. But as like a residential customer, you can't just put up a ton of solar. Yeah.
Doesn't like you have like the photovoltaic cells on your house? It's not like you can use it electricity, don't you like sell it back to the power company?
Yeah, so you're not necessarily using that yourself. It just kind of goes into the electric grid, right? So those are two different scales of PV solar. Solar heating. Anybody have like a pool cover that's supposed to heat your pool? I don't even have a pool. I don't know. But some people do have pool covers that are supposed to heat your pool. That would be a passive solar heater. But we can do large-scale solar heat, as we'll talk about in a few minutes also. All right, we don't actually need to know very much about these photovoltaic cells. I want to say a little bit. I know a little bit more than I'm going to say, so maybe later on we can take questions. We don't need to know very much at all. What I want to present to you is that some materials exhibit an effect called the photoelectric effect. And those materials can absorb light and send electrons, right? And do electric current, right? Make electrons move as a result of that light, right? So that's called the photoelectric effect. That effect has been known about for closing in on 200 years. And the first photovoltaic module was made in Monmouth County, in the 50s, right? Belleville, right? Yeah, so that's pretty cool. I can pass some around. So first of all, is my light lit? Is it? You're seeing it as this little red light. Is it on?
Yeah.
I hope you've been able to see it. So that is powered. If you look how cloudy it is, that's powered by. Alright, so show it so the other section can see it too. That's powered. Probably is it on still? I don't know if there's as much light hitting it now. Am I aiming it well? Alright. So other section, when this is in the window, this little red light does light up a little bit. This one.
My house is actually.
So let me pass some of these around. These ones are just really garbage. These are, I think I bought these my first year here, and they lasted for a little while, but they just really can't withstand
My dad
much
used to
use.
It's
Right.
like
So it's like the kind of shiny blue stuff inside. That's the actual photovoltaic panel. But I couldn't get any of the little motors to turn. I used 2 incandescent bulbs. I couldn't get the little motors to turn. So go ahead and try, but don't expect to have much success. Right, so here's some photographs of some of these photovoltaic panels. These are ones that are on somebody's roof, right? These are ones that are laid out on the ground. Like the Tinton Falls one kind of looks more like this. And we usually would connect these cells together in series with each other, so that the potential difference that each one is generating would add together, right? And ideally, we'd want them to be in kind of 120 volt amounts, but we don't necessarily get that. So what we do need to know, we definitely need to know the energy conversion that's taking place in both of our types of solar power. For solar photovoltaic, we really do just have light energy changing directly into electrical energy. So this is our kind of one form of electricity production that doesn't involve a turbine and generator. Right? The photoelectric effect allows the light to be converted directly into electric. We definitely have degraded energies for this, right? There is going to be heating up of the panel itself. There's, I'm sure, others as well. I don't have a great efficiency value for you. I spent a lot of time trying to find it, and I found very little. Probably less than 12% efficient is as good as I could say. So what does that mean? That means that the light that's hitting it, potentially 12% of that energy could get changed into electric. So in addition to heating of the cell, I don't think these things work equally for all wavelengths. There's a temperature dependence light's going to get reflected. I mean, I think there's a number of different ways that the efficiency could be impacted. And I do see the hands, just give me minutes though. Beyond the efficiency, we also need light for these things to be making electricity. We can't do it at night. If it's cloudy, we can't do it very well. We don't have a great way to store the electricity that these are generating. So we kind of have to use it as it's made, or at least let somebody else use it, pump it back into the electric grid. All right, so I think I'm done with photovoltaics. So yeah, I'll take questions on that now, Isaac.
So you say you know more. I've heard that it is more efficient to have with the big areas of solar panels. You have a bunch of mirrors shining the light onto one solar panel than having all those solar panels spread out.
I'm only familiar with that for using solar heat, not solar photovoltaic. But I can't say it doesn't happen, but I'm only aware of doing that for solar heat, and we're getting to that in a minute. Yeah, Leo.
Can you combine solar heating and photovoltaic?
Can you combine solar heat and solar photovoltaic? I mean, I don't think you could use the same light to do both. You could use, I mean, like, I know in Hawaii, some people do have solar heating panels on their roofs, like to help them with hot water. As far as I know, New Jersey doesn't have any limitations on what you can do with solar heat, but I don't think you can, like, use the same light for both. All right, so good, on to solar heat. All right, so solar heat just means we're using, like, heat, not light, but thermal energy to do something, right? And often it's just heating water. So heating swimming pools is a pretty easy way. But I just mentioned in Hawaii, some people use solar heat. That's not for electricity. That's just to help heat up like their water heaters, so they're not using electricity to make their hot water. It's probably not enough to heat their water as hot as they want it, but it can help out. And the heat we can store. Right? The photovoltaic electricity we can't store very well. The heat we can store just fine. So here's a picture. Let me turn off one set of lights to see this a little better. And actually, at first glance, it doesn't look that different from a solar photovoltaic panel. It's like dark, it's shiny, it's got a blue tint to it, but it's totally different, right? We see these like linear features. Guess what those are? Pipes, right? Those are pipes. So those are pipes that have a fluid in them. Water would be the easiest thing to use, but it doesn't have to be water. So we are just kind of letting that water cook in the sun for a little bit, and then bringing it somewhere else to use that hot water or hot fluid for something. So yeah, so each of these pipes, I would sit there for a little while, maybe we're circulating the water really slowly. That's kind of it. That's really all there is to it. So the energy conversion here would be like, I suppose you could say radiant energy, right? Into heat, into thermal energy. What's that?
Doesn't have to be really efficient then.
Well, dude, so you said they have to be really efficient. I don't know about that, because they can heat up the pipe. I don't know about that. Are they really going to absorb all of the light? Are they going to reflect some? Are they going to re-emit some? Are they, yeah, I don't know. Now, it is possible to change heat into electricity. There's a device called a thermocouple that I think we encountered with a classwork question a few classes ago. But the only places I'm aware of that try and do solar heat into electricity actually use a turbine and a generator. All right, so here we see, I'll turn the lights off again. These are all mirrors, kind of like what Isaac was talking about. These are all mirrors that are attempting to redirect sunlight to this really bright thing up here. So that's like a glass chamber that will flash boil water, drive a turbine, drive a generator, boom, electricity, right? So there are some kind of large-scale solar heat plants. I've never personally seen one, but there are a few in existence. All right, so how much power are we talking about? For photovoltaic, as of last year, I'm sorry, I was lazy, I didn't look stuff up again this week. As of last year, 250 megawatts was the biggest photovoltaic farm that I could find, and that was in California. I wouldn't be shocked if there were, actually I would be pretty surprised if there are bigger ones now. I only found 8 others in the world that were over 100 megawatts. I would bet we have 1 or 2 more this year. For solar heat, I found actually a more powerful plant than this one, 354 megawatts, also in California. I found 11 others that were greater than 100 megawatts, but all of them were in Spain. Right? The
Barcelona.
biggest one was in Spain, and then, I'm sorry, the biggest one was in California, and the rest of them were in Spain. I don't know why that is.
Because we said we can do it better than we did.
What?
No.
Oh, you think this, oh, no, I don't know that the Spain ones came before the California one. I don't know that happened. All right, so let's look at advantages, disadvantages, and then I actually do want to eke our way through a couple of the more difficult objectives when it comes to solar. All right, advantages, right? We already talked about some of these. Renewable. We're not going to run out of sunlight. Sunlight continually gets replenished as we use it. We can use solar in rural places, right? If you live like in Wyoming, like where there's like 20 miles until your next neighbor, power plant's not going to get built there. Nobody's going to put a coal burning power plant or a nuclear fission power plant there. There's not enough customers. They have to send that electricity too far away to have enough people to sell it to. So we have a problem, but we can use solar. Right? We don't need to rely on somebody big to put that in for us. No emissions, right? The light is free. Those are the biggest advantages I could think of. Disadvantages, so the efficiency we said is very low. Energy density would be quite low as well. What else do we have? Because of these reasons, we do need huge surface areas to generate like a reasonable amount of electricity. And obviously it needs to be sunny. We do have that storage problem. So it needs to be sunny both like in terms of daytime, but also the time of year plays a role as well. All right, other issues with the solar photovoltaics or the solar heating before we start looking at this light that leaves the sun and reaches us and like how much reaches us and how much we can do with it, and the other questions about the kind of mechanics themselves. Good. All right, I was rushing a little bit, now I'm going to go a little bit slower. The sun is extremely powerful, right? The sun does fusion and it does a lot of it, and its average power is about 4 times 10 to the 26th watts. Right? That is a ridiculous amount of power. But obviously, only a very small amount of that power will hit the Earth, right? Because we're pretty far away and we're pretty small, right? So the total power of the sun is this, but the power that reaches us is going to be way, 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 way smaller. And guess what we need to be able to calculate? Yeah, how much power hits the Earth, right? And it's actually not that bad of a calculation, and it's kind of a fun calculation, right? It's kind of a fun calculation. So the sun's light, I was going to turn this on, but that's just going to be irritating. I'll just turn it on for a minute. All right, so we'll pretend this is the sun for a minute. The light goes out in every direction, so that power kind of leaves the sun as an ever-increasing like speed. It goes out in like every direction. Every direction, right? All 3 dimensions. So that power kind of stays constant. Well, unless the light hits something. But it's it's getting weaker and weaker and weaker because that power has to spread out to encapsulate an ever-increasing speed. All right, so a tiny amount reaches the Earth. All right, here we go. So what's the? I don't want this up here yet. Whatever, it's fine. So we have the sun. Right, the power goes off in 3 dimensions, not just 2 dimensions. So we're talking spheres, not circles. And we actually need to care about the volume that power will fill. So how do we find the volume of a sphere? I heard some 4s, I like that.
Pi.
I like 4/3. I heard a pi, I like that.
Or radius squared.
Radius cubed. Alright, so volume of a sphere is 4/3, well, volume of anything has to be meters cubed. So 4/3 pi r cubed is the volume of a sphere. Right? So this 4 times 10 to the 26th watts, right, encompasses this a sphere, and we have to consider the volume of this sphere. Now, how are we going to do this? I'm looking for a sphere. I don't particularly want to use that, but I will if I can't find something else. Here's a better one. Actually, looks kind of the same. What do you see?
Blue.
What shape do you see?
Sphere.
You do not see a sphere.
Circle.
You probably don't see a sphere. We do have stereoscopic vision. You are looking at it from two slightly different directions. But if you do, what do you call it, cyclops, right? One eye. If you do cyclops, you definitely see a circle, right? You know you assume it's a sphere, but you only see a circle if you do cyclops. So the sphere of light that leaves the sun does hit the Earth eventually, but all we actually care about is the surface area of the circle of the Earth, not the surface area of the sphere. Because sunlight only hits once it gets hit, it doesn't hit anything else. So it's a circle that's blocking that light, like no light hits the back, right? It's a circle that's blocking the light. So if we want to find how much of the sun's power hits the Earth, right, we need to care about not the surface area of the sphere, but the surface area of the circle that is the Earth. All right, so that's some geometry. That's the volume of a sphere, and this is surface area of a circle. I hope I'm not getting myself into trouble. How am I doing? Yeah, I'm doing okay. Doing okay. Doing all right. Yeah, I don't want to take questions yet. Let me finish, right? Maybe I dug myself a hole. I don't think I did. But let me finish, and well, what?
How does it?
Yeah, let me finish. So we have the light that's leaving in a sphere. It hits the Earth, and the Earth looks like a circle to that light.
But doesn't it not look like a circle to that light?
It absolutely looks like a circle. Why not? It looks like a circle to the sun, I guess I could say.
Because it's a sphere, which means that.
Fine.
So even if it looks like a circle, or is perceived by a circle, light is hitting half of the sphere, not a circle.
It's hitting a circle. It is hitting a sphere, but it's the circle that catches stuff.
But isn't it half of the sphere that catches stuff?
Fine. So what?
So it would be 2/3 higher cubes.
Are these are not the same size. Are these the same size? Those are darn close to the same size, right?
Sure.
I think.
Yeah.
But it's
Okay. Who? If I'm going to orient them like this to care about the overhead lights. Who catches more light? The same. They should catch the exact same amount of light as each other. All right. So go ahead, argue. Because I think that's as good as I'm going to get in terms of explaining it.
But it's extended outwards.
So what?
So it's
These catch the same amount of light. These both. If I hold these in front, oh, that's not going to work. I'd have to do it with the projector. If I hold these the same distance away, they should produce the same size shadow because they're both blocking the same amount of light. That's as good as I can do. If that doesn't work, I'm sorry, but I failed. No, we haven't calculated anything yet. We haven't calculated anything yet. So let's see what else I have here. The sphere of light that's left the sun, right? That we do care about that surface area, right? And that sphere. Because we don't really care about the light that continues to be generated every moment. Like we want to know, all right, how much of this 4 times 10 to the 26 watts of power hits us right now? So we actually don't care about volume. Maybe I did mess up by incorporating volume. But we do care about the surface area of that entire sphere. So we need to care about the surface area of the sphere of light that's left the sun. And the radius that we would need for that would be the radius of that sphere, the orbital radius of the Earth. Right, so I'm calling that RO for orbital radius. And then the only amount of light, the only power that strikes the Earth would be this circle that the Earth appears to be from the sun, where the R would be the radius of like the actual Earth, like the core of the Earth to the surface. Right. Those are the only two values we need. And all we have to do to find the fraction of the sun's power that hits us is divide, right, that surface area of the circular Earth by the surface area of that sphere of light that left the sun. Right? And that will give us the fraction of the 3.9 times 10 to the 26th watts of power from the sun that left. So I want to do that calculation, except I didn't give you either of those values. Yeah, I mean we need those, right? So let's look those up. Maybe did I give it to us? No, I didn't give it to us. All right. oh come on, by value of pi.
You don't need pi, you cancel that.
Well, that's true. You actually don't need that. All right. So first, let's get the orbital radius of Earth.
Now you can.
And I'm actually gonna want you to do this in your foursomes. So those of you that are rushing to calculate, just like relax. All right. Orbital radius of the Earth: 1.5 times 10 to the 11th meters. Okay. 1.5 times 10 to the 11th meters. I'm gonna write that down too because I want to do the calculation. So that's like this RO that we said, and then I feel like I should be able to remember the radius of the Earth itself, but I can't. We can do two significant digits. 6.4 times 10 to the 6th meters, right? All right, so in your foursomes, please try and find what amount of power from the sun hits the Earth. Now it's spread out everywhere, right? But this is going to be the total amount of power striking the Earth.
Yes.